Now we're starting to get into some real statistics. Hi. We're starting to get into real work with statistics where we use it to infer certain knowledge about the population that we draw samples from. So tonight, we're going to start to talk about what we really do in statistics, which is create studies, take samples, and make some inference from those samples. In other words, what do we know about this population? How sure can we be about what we know about this population from what we did with our samples? Well, one of the things I'm going to start with is this document called Introduction to Sample Distribution and the CLT. Anybody know what CLT stands for? What's that? Central, yeah, you got it right. Central limit theorem, right? Okay, well, we'll talk about what that means. We're going to talk about sampling distributions, how samples behave. So we have this document, Introduction to Sample Distributions and CLT, and we have a corollary Excel file also. Let me see if I can't get to that easily. Yep, I lost Blackboard here somewhere. There we go. And let's see, doc. Here it is, population of 100. I'm going to open this Excel file as well. And it's just the same file that you see, the same distribution that you see in that document, that Word document. There you go, same thing. Imagine this is a population, right? Now, a lot of times when we talk about populations, we mean something really big. All the people in New York, all the people in the United States, all the diabetics, all the people with heart disease, all these and so on and so forth. It doesn't have to be that way. I mean, a population could just be all the students at Hunter, all of the students at School of Public Health, could be all of the students that are taking Bio 610, right? That could be our population. Population just means that it's everybody that fits within that criteria that we define as part of this population. This particular population is normally distributed, take my word for it, okay? And there are 100 people in this population. The way I've laid it out here is in rows and in columns. There are 10 rows and there are 10 columns. So we can identify any subject, any individual subject in this population as row number 2, column number 4. Their score was 45, right? Whatever this happens to be. Blood pressure, no, obviously not blood pressure, but score on an exam, normally distributed scores on an exam, some blood measurement, some whatever this might represent. We really don't care at this stage. So rarely do we get to see an entire population laid out in front of us like this. We're going to get the census done in about another year or so. And when the census is done, we're going to have data about everyone in the United States. Not a lot of data, a certain amount of data about income, about family size, so on and so forth. But we won't, that's population data. We're counting everybody in the country. That's very rare, right? In fact, in the United States, we only do it once every 10 years. And it's a monumental task and a political hot potato on top of that. So we're going to look at using this small population. We're going to look at what happens when we take a sample from a population. How good are we at predicting what that population is like from a sample instead of from the population itself? So the first thing I'm going to do is I'm going to take a look at our population and I'm going to calculate what the mean of the population is. Mu, right? In other words, the population mean. I'm using mu because it's a population parameter. Okay, so that's going to be equal to the average of all of these values. Okay, and it turns out that the average is 50. Okay, I'm not sure, I don't know how many decimal places I've reserved for that particular box, but that's what we happen to have. So now, I mentioned as we started to talk about the normal distribution that with normal distributions, if I know two important properties of that normal distribution, it tells me an enormous amount about the way that values and subject values are distributed in that population, right? One of them was the mean, the middle of it. It's a description of where the middle is. The other one is the variability within those values. In other words, the variance or the standard deviation. Okay, in this case, since it's a population, I'm going to call it sigma. It's everybody in the population. So I'm going to call it sigma. You can see the mean, which is a little bit different than 50. So how do I calculate that? That's going to be equal to the standard deviation of the entire population. And let's see what that comes out to. Oops. I hope I didn't mess that up. Oh, okay. It's about 9. So our mean for this population is about 50. Our standard deviation, our variability or standard deviation, is 9. Tells us a lot about this, right? For instance, it tells us that approximately 68% of the population is between 41 and 59, right? What was that called? You remember what that's called? That's called the empirical rule, right? Okay. And it also tells me that, let's see, double that, 2 standard deviations, 95% of this population is like, if it's normally distributed, it's likely to be between 32 and 58, 68, right? 95% of the population. You guys remember that, right? From this part of what we did on the homework, on the tests, and so on and so forth. Big part of what we've been working on up to this point, right? So, it tells me a lot about this population. Just those 2 numbers alone really fill me in on a lot of information. Okay, so now, problem is that I rarely, if ever, get to know what that is, right? In order to know the population mean and the population standard deviation, I have to measure everybody in my population. So if I'm doing a study that involves blood pressure of diabetic seniors between 60 and 80 in New York City who have diabetes, right? Well, how many blood pressures do I have to get? Well, geez, seeing there's 9 million people now, I think, in New York, and between 60 and 80 might be, I don't know, a million of them. And how many of them are diabetic? Maybe 800,000, or a million of them are diabetic in that age range or something like that. So in order to know what mu and sigma was for that small, narrow population I picked out, I'd have to go out and measure the blood pressure of 800,000 people, or whatever I mentioned it was. I forget already, right? So that's going to be kind of cumbersome and expensive. So how do I get around that? I get around that by saying to myself, if I can randomly sample a small portion of those 800,000 people that fit my population description, well, maybe that'll give me enough information for me to predict what the mean of the population is and what the variability in that population is, just from the people that are in my random sample. But it's important. Sample has to be random. The people that we sample in this, our subjects, have to be independent of all our other subjects. Each selection has to be random and independent, right? We have to be absolutely sure of that. We don't want this messed up or confounded by a sample which is not random, which is biased. In other words, if we're going to take 100 people in our sample, and 90, and we sample an area of the city where, or a nursing homes where most of the occupants are women, and we wind up with 90 women, only 10 men in our sample. Well, we kind of biased. It's not really a random sample. We kind of biased our sample. Right, so you got to really make sure that it's representative of the population. But in any case, we're not going to be able to sample the entire population. So we need to wrap our heads around, well, in that case, how can I trust my sample? In other words, how big a sample for our 800,000 people who are senior diabetics? How many people do I have to sample in order to have some kind of an idea, some sort of assurance that the average of my sample really predicts the average of the population? Do I sample 10 people, 100 people, 1,000 people? We can all agree that the more people we sample, the more likely it is that we're going to wind up with something that really represents the mean of the population and the variability of the population. right? Big sample, more reliable than a small sample is, right? Everybody nod their heads. I know you agree with me, right? Okay, good. All right. So the thing is, when we take samples, we have to say to ourselves, okay, so now let's say I decide I'm going to take in this population here, which has 100 people in it, I'm going to sample 9 people from this population, right? Okay, so I'm going to take a sample size of 9. So I said to myself, okay, gee, if I take a sample size of 9, I'm going to randomly sample 9 people out of these 100 people. I'm going to take the average and the standard deviation for those people. And I'm going to say, well, gee, here's our sample mean approximates our population mean. It's not very precise. The idea approximates, right? And our sample standard deviation approximates the population standard deviation, sigma. Again, that's not very precise. I need to pin down how likely it is that I have a good estimate of our population mean. So what we're going to do now is we are going to do a little experiment where we're going to take a sample of size 9. We're going to take it once, randomly sample 9 people here. We're going to do that once, okay? And see what we get. Then we're going to do a second time. Then we're going to do it a third time. Then we're going to do it a fourth time. Then we're going to do it a fifth time. And however number of people I can convince to do it online, it's tough. I don't have them in front of me to reach out and grab them by the neck, make them do it. But maybe I'll get a couple. Maybe I'll get a couple to do it for me. Yeah, that's just the network, whatever's going on with the network. That'll pop up and go away every once in a while. Okay, so we're going to take a random sample of 9 people. Each one is going to take a random sample of 9 people. Problem now is, how do we take a random sample, right? Do I just, like you ever seen the old detective shows? They take the phone, but you don't have phone books anymore. We take the phone book and they just, go something like that or something, to call someone at random. Well, we don't have phone books anymore, so we can't do that. How do we do this? Well, we can't just do this. I mean, if you're right-handed, you may pick more people on the right side. If your right eye, if your stronger eye is the right eye, trying to do it randomly, as humans, we're innately gonna bias the sample one way or another, right? So we need a mechanism for taking a random sample. You can do that with computers now. You get computers that take these various values and randomly sample them, right? That's kind of doesn't seem, like doesn't make any sense, right? To write a program, do something randomly, right? Kind of doesn't, seems like a built-in contradiction, right? But they do have programs that do that. In the old days, which is what we're going to use right now, I don't need this. In the old days, what we might do is we might go to a random number table. Does that keep popping up? Oh, okay. Okay, this is and we have this on Blackboard. This is a random number table that's on Blackboard, and you get a whole introduction here. There might even be one. I don't know if there's one in our text. I don't think there is. This is from some statistical text. That's random number table. These are numbers that were generated randomly. Okay, just single digit numbers, each one of them generated randomly, either by a computer or some other mechanism. There's even random number tables that are generated based on radioactive decay. The randomness of the relative randomness of radioactive decay and particle counts and so on and so forth, the frequency of particle counts. And they're normally distributed, but then you can figure out how to use that to create random numbers. So there's many, many different ways to create random numbers. This table, it might even say how it was generated somewhere in here, but I wouldn't count on it. I'm not really, we don't really care about that right now anyway. But what I can do with this random number table, this generated random number table, is I can start somewhere, anywhere, like right here. I'm going to start right there. And I am going to take that string of random numbers and I'm going to use them to determine the numbers that I'm interested in, these people in this population I'm interested in. So the first person is going to be row 5, column 3. Second person is going to be row 0, column 1. Third person is going to be row 0, column 9. Fourth person is going to be row 4, column 6, and so on and so forth. See what I'm doing there? I'm just following it right across to get a random sample from that population, which is better, probably going to be more reliable to give me a random sample than doing it by hand. Everybody okay with that? Okay, so what I'm going to do is,
The first number you said is the row and the second one is the column?
yeah,
Okay.
you want to do it your way, you can do it the other way too, because it doesn't matter, right?
Okay.
It's going to be random anyway. So I'm going to blow this up a little bit. I'm going to try and figure a way to get both of these on the screen at the same time. See if I can't do that. First, let me get rid of the sidebar. Okay, that's, I don't have that. Okay, hang on a second. View, hide the thumbnails. No, hide sidebar. Good. I'm going to narrow this. Oh, that didn't help. That was not so good. Okay. Okay, how about that? Good. I think that we might be able to get away with that. And then I'm going to put this over here. Okay, so what I'm going to ask you to do is, I need to give you more of these because I don't want you all starting at the same spot. Start in some random spot, like in here. I'm going to start in some, in other words, don't start at the beginning of a row. Start like here or something like that, or start like here. Start anywhere you want and then just go from there. And pick out 9 values based on that. Like if I start here, I'm going to pick out 005, which is going to be 27. And the next person is going to be 20, which is 48, and so on and so forth. So pick out 9 people randomly and calculate the mean and the standard deviation for those 9 people.
Sorry. You started, you did 05, 20. Does
Yeah.
it really matter if you were
4-3.
like 4-9, like you wrapped?
Oh, no. Yeah.
Doesn't matter.
No, do it. Do it. Yeah, they're all random, so it doesn't matter what direction. You go backwards if you want. Right? You can start at 9-8, 6-9. You can do it any way you want. I just don't want everybody doing the same thing because then we will not have 5 samples. We'll only have 4 or 3 samples or something like that. And I'm going to do the same thing.
I don't have a computer.
Do it in hand.
Standard deviation?
Huh? No, just do the mean. Don't do standard deviation.
Okay.
Don't do standard deviation. Just do the mean. Okay. And then you can rely on us to do that. Actually, yeah, don't worry about standard deviation. We're going to play a little trick with that anyway. So I'm going to do this also. So, okay. So where was I? I'll start there. 61, 49. 04, 58. Where was I? Already lost myself. It doesn't matter. 40. Oh, great. What happened here? Oh, I know what's happening. It's too far over. Okay, that's okay. Okay, so I'm gonna add all those together and I'm gonna find the average of all of these. Then I'm gonna find the standard deviation. If you don't have a computer or a calculator to do it, don't worry about standard, just find the mean. Okay, and you guys at home, if you're playing along with us, if you want, you can type into the chat box the numbers that you got. So that's my average and my standard deviation.
We're looking for 9 numbers.
What's that? 9 numbers.
9 numbers.
Okay, and if you got it, if you want to yell it out, I'll take the average and the standard deviation. I'm sorry, 40,
47.4.
good?
I have, mean of 49.22,
I'm gonna round off to 2.
and a standard deviation of 9.18.
Got no takers at home? Oh, I got a 50. Okay, wow, that's a fortunate one. 50. And did you calculate a standard deviation also, Rafaela? Oh, give it a try. If you have a computer handy, you do it with a computer. If not, don't worry about it.
It's in Excel. There's an Excel.
Got one more out there?
I got a mean of 48 and a standard deviation of 7.
7, wow,
Wait,
okay.
what do you mean, zero?
When I got a 56.2, okay.
I see.
If you don't, standard deviation is secondary, I don't really need it that much, but the means, I would like to get a couple more means. 1, 2, 3, 4, 5, 6. 3 more means would be really good. I may cheat and just do a couple this way. Simply because I think they're random anyway. So I got 1, 2, 3, 4, 5, 6. 1, 2, 4, 6, 7, 8, 2 more.
Or what?
STDEV.
SEDEV.
5.
That's,
Yeah. Is that what you?
yeah. And what did you get?
9.18. You got 7.
7.1259.
So should they be close to?
We'll see.
It is?
We'll see in a second.
Okay.
I did already. So you just said with the range and the range.
Of all the numbers.
Yeah.
Yeah. Mhm.
Okay, So I've got 9 means, 9 randomly selected I've got 9 means from this population, of samples from this population. And I got a couple of standard deviations also. What do I notice about the numbers themselves? Well, we got a 61, we got a 49, we got a 63, we got a 37, we got a 59. They're pretty variable, right? There are a lot of them that are a lot different than 50, right? But when I took a sample of size 9, right, what were all of my results closer to than the range in the actual numbers themselves? They're all closer to the mean of the population. So if we take a random sample from a population, even size 9, it approximates the mean of the population. Okay, what about this? A couple of standard deviations I calculated. 9.37, 9.18. What was the, it's also similar, right? So the mean of our sample, X bar, right? X with a bar on top of it, approximates mu, right? And standard deviation of our sample, right, approximates sigma, right? Okay, that's what we're after. That's why we're taking a sample, because we want to understand the mean and the distribution of this population.
What happened in Freddy's case where he got like sigma of 7, I mean standard deviation of 7?
Well, what's going to happen is that sometimes you're going to be higher, sometimes you're going to be lower. Sometimes, occasionally, rarely, it'll be an extreme difference, right? So in other words, here we got a mean of 56. That's quite a bit different than all of these others, right? But that happens. How often does it happen? It was only 1 out of 9 times that it was that extreme, right? But that can come up. I mean, now we have to say to ourselves, well, if I only did it that one time, that would have been a problem. I would have been way off from the mean of population, right? So I need to understand this dynamics of sampling. I need to understand this a little bit better. Let's do something interesting. Let's take the 9 times that we sampled this population and find the average of the 9 times that we sampled it. So the individual samples went from 46.1 to 56.2. So let's find the mean of all of the means. Okay, the mean of all of the means is equal to 49 point. Boy, it's remarkably close, isn't it? Right? And let's find the standard deviation of the means. What do you think we're going to get there?
Closer to 9.
Whoa.
What happened? Interesting. What was the standard deviation of the population again? What is this? What's the relationship between those two numbers?
It's a multiple.
Square root.
Oh.
It's a square root.
Yeah, that's right. It's the formula.
Okay, now what happened here? What happened here? When we take repeated samples from a population and we create a new distribution of those sample means, a whole new distribution, 50.8, 40.7, we do that 10 times, 100 times, 1,000 times and make a new distribution, it's going to have approximately the same mean as the population mean. But now, because the samples that we have, have like eliminated the extremes. In other words, we're not going to get a mean of 9 people. That's 36. Because there aren't even 9 people that are 36. We're not going to get a mean of 69, right? Because it's going to even it out just by virtue of being a sample of size 9. So the mean of the sample distribution, this new distribution that's created from repeatedly sampling the population with the same size sample, and then making a new distribution, this new sample distribution is going to approximate the mean of the population, right? But the standard deviation of that new sample distribution is going to be equal to the standard deviation of the original of sigma divided by the square root of the sample size. That's really what it's going to be, equal to. So mu is going to approximate, the sample distribution x bar is going to approximate the mean of the population, but the standard deviation of our repeated samples is going to be equal to the sigma divided by the square root of the sample size. Right? It's really square root of that. They're really what's going on is not really the square root of that actual number, but it's square root of the sample size. So sigma was 9, sample size was 9, square root of 9 is 3, so 9 divided by 3, and this actually predicted it pretty well, right? And I didn't pull any tricks here, right? We did it just, you saw us come up with these numbers right in front of you, no magic, right? Right, this is the real thing. I mean, be honest with you, sometimes when I do this at this point in the course, it doesn't always come out this well, but you can see what happens there, right? Now what if I increase the sample size? If I increase the sample size, the standard deviation of the sample means becomes smaller. The variability of our samples becomes smaller. In other words, and what that variability really means is, if this is our, oops, come on, there we go. Got to wake it up. There we go. Nope, I'm not connecting. Okay. So this is our sample, this is our actual population, right? 50. And I think one standard deviation was 9 below, which was 41. 2 standard deviations was 32, and so on, right? So that's our, so mu is equal to 50, and sigma is equal to 9, right? Now, if we took repeated samples from this population, now we still have a mean of 50, right? But now our repeated samples, the values we get for our repeated samples, is going to be narrower, like so. And the standard deviation for our repeated samples, well, that's going to be equal to the sigma, right? Sigma divided by the square root of our sample size. Okay. In this case, divided by the square root of 9. So it's going to be 1/3 as wide as the original population. What if my sample size had been 16 instead? What would happen? Square root of that is 4. It would have been 1/4 as wide. What if our sample size was 25? It'd be divided by 5. 100 would be divided by 10, right? So this gets narrower and narrower. Our sample gets closer and closer. The variability in our sample means becomes smaller and smaller as we increase our sample size, right? So that's a good thing, because that means that by increasing the sample size, we make our prediction about the mean from our one sample more reliable than if we took a small sample. Okay, bigger sample is the more reliable we get. So let's move on from here to some exercises here, some ways to maybe apply this. Oops. Okay. 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 So to reiterate what we were doing, before we really apply this directly, I want to just reprise a little bit of what we did on our last session about the normal distribution. Okay, and this might help a little bit on the exam or on one at home. Somebody had a question about this, something very similar to this on the homework. If total cholesterol values for a certain population are approximately normally distributed with a mean of 200 milligrams and a standard deviation of 20 milligrams per 100 milliliters, find the probability that an individual picked at random from this population will have a cholesterol value between 180 and 220. Well, okay, let me just sketch that. Okay, and I'm not sure why I can't get this to. Up there, it's working now. Okay. Okay, so what is that going to look like? Here is our normal distribution, little funky. Whoops. And this, I keep forgetting I got to switch. I'm using a different way of doing this. Okay, and 220. And then, okay, 220. So our mean is 200. And our standard deviation is equal to 20. Okay, we're talking about our population now, right? Sigma, mu, and sigma. Okay, so, and we asked, what's the probability we'd pick an individual out from this population who has a cholesterol between 180 and 220? Well, we know that that is one standard deviation below the mean, one standard deviation above. So that is 68% of this population is between those two values, empirical rule. So I really don't have to go to a table or anything like that if I'm willing to, approximate it, and not only do I know 68% of the population is between those two cholesterol values if it's normally distributed, but I also can say, phrase this another way and say, the probability of me randomly selecting a person from this population and their cholesterol being between 180 and 220 is 68%, because that's what percentage of the population has that cholesterol. Okay, so now what's the next part of this question? Let's take a look. Okay, between 160 and 240. Anybody want to hazard a guess on that? Two standard deviations above, two standard deviations above can be 95%, right? Empirical rule, right? You're scaring me here because I don't see a lot of recognition in this. Okay, good. A yes goes a long way. Trust me. Okay, so 160 to 240,
97.
95.
95.
Right. Now, at three standard deviations would be 99.7%, right? Okay, you had the right idea. Okay, so what am I going to do? Where do I go from here? Okay, well, next we're going to complicate this. Of course, what we do is we complicate it a little bit. Yeah, 225 and greater than 225 and less than 150. Okay, so greater than 225. Greater than 225 is about there. Okay, greater than 225, it's about there. Okay, that's 225. And we want to know what percentage of this population is greater than 225 and less than, what did I say? 150. Okay, about down here. 150. We want to know what's in reds here. I'm going to start with less than 150. Well, I need to know what area is below 150. In order to do that, I need to know how many standard deviations away from the mean the value 150 is, the cholesterol 150 is. We gave that a name, number of standard deviations, right? We called it the Z-score, right? So, yep, we can look at the Z table. Well, first let's calculate what Z has to be. Z is the value we're interested in minus the mean, difference between the value that we're interested in, the mean, divided by the standard deviation. That's the number of standard deviations, right? So that's going to be 150 minus 200 over 20. That's going to be equal to minus 2.5, right? And if you do it this way, this is 150, this is 200, so naturally comes out to be negative, which anything to the left of the mean is going to be a negative Z-score. So now we go to our table. Okay, oops, let me look it up. I'm sure it's on Blackboard. I'm just going to search for it here. Or we can also use Excel, of course, if we wanted to. And here we go. Why don't we use Excel?
No, how can we?
Oh, I'll do both. I'll do it both ways. Okay, so in this case, we are interested in
Negative 2.5.
-2.5. So go back to pointer here. Okay, -2.5. And what's the third digit? 0. So it's the first column, right? 0. The third digit is 0, right? Negative 2.5. If it had been negative 2.53,
Then go.
0, 1, 2, 3, it would have been 0.007. But in this case, it's equal to 0.0062, 0.62% or 0.0062. So I'm going to go back to my table here, and this area is going to be equal to, this area here is going to be equal to 0.0062. That's the proportion, right? As a percentage, it would be 0.62%. Okay, so what about greater than 220, greater than 225? Let's figure out the z-score for that. Z is equal to 220, 225 minus 200 over 20 is equal to 25 positive over 20 is equal to 1.25. Okay, so let's look up the z-score for that. Well, that's going to be, oops. That is going to be the second page of the table, right? Here's our table. That is going to be second page of our table, which is the numbers above that, which is going to be 1.25, 1.20, 2, 3, 4, 5 is 0.8944.
Wait, do that again, I'm sorry.
1.25, 1.20,
Okay, okay.
1, 2, 3, 4, 5. I'm doing that because I can't see, yeah, right, 1.025, right, 0.025, 1.02, 1.25, rather. Okay,
0.89.
right, 0.8944. So I'm going to go back to our table, 0.8944. So we'll go back to the pen. And this is, well, wait a second. It's not this area, is it? It's always the area from here down, which is 0.8944. That's not what we're interested in. We're interested in the area above that value, right? Greater than 225, right? Remember what the question was. Find the probability of the percentage of people, or probability of selecting someone that has a cholesterol below 150 or greater than 225. So when I use the Z table, it always gives me the area to the left of the value that we're checking, right? Okay. In fact, you can see that if I go back to the table, if I look at the second table, the one for the if I look at the second table, notice how the z-score is all the way over here, and this is the area that it's giving you. So for the if the z-score is positive, it's always going to be an area greater than 50%. If the z-score is negative, it's always going to be to the other side of the mean, so it's always going to be an area less than 50%. Okay, so if I go back here to this, and I look at this, that's 0.8944. Well, what does that leave here for the area that we're actually interested in? Well, it means that that's equal to 0.1056, right? 1 minus 0.8944, right? So,
I'm sorry, question I had from you before.
Yes.
When you initially did that formula, when you got the Z equals X minus M of the standard deviation, where did you get the 225 from?
it was in the question.
That's value that we want.
Yeah, let me get back to the question there. Where's the question? Okay, let me see if I can't scroll up here. I got to change to the pointer again. Let me get it up there so you can read it. Find the probability an individual picked at random from this population would have a cholesterol greater than 225 or less than 150, right? So those are the two values that it was asking for. So what's the probability that someone would have a cholesterol between 150 and 225, right? Well, yeah, you add these two together, right? You add together, you add 0.1, whoops, what happened there? There we go. You add together 0.1056, which is this area, and you add that to 0.0062 and subtract all of that from 1, right? And that leaves the area in between, the probability someone have a cholesterol between 150 and 225, right? So it's just playing with the geometry of this distribution.
Wait, why do you have to subtract it by one? Why can't you just add this?
Well, I add them together because the question was, what's the probability of selecting someone that's between 150 and 225?
Oh, never mind.
Yeah,
Okay, sorry. I
not,
was thinking-
yeah, you had the right answer
Yeah.
to a different question,
Okay.
right? The answer you had, the question you answered was, what's the probability of being either less than 150 or greater than 225? In which case you would just add them together.
Right, okay.
But if you want to know what's between them, you would subtract it, add them together, and then subtract it from one, because that's what's left. That's why it's always good to sketch this stuff, because it'll really help you avoid making mistakes. Okay, let me clear this. Okay, and go back to the questions. Okay, so, and the next question is between 190 and 210. You're gonna do exactly the same thing. You're gonna find the area, that's less than 190. In other words, 190 minus 200 over 20, which is negative 0.5. You go to the table, find the area less than that, and 220 minus 200 is 10, is going to be plus 0.5. You're going to find the area to the left of that, right? And so what did we accomplish there? Let me see this. Let me see what we accomplished there. So in that question, if you wanted to know the fastest way to find out what's the area between those two, right? Here is the mean is 200 and 190 and 210. Okay, but we're interested in knowing what this area in here is, right? So when I look up the z-score, when I calculate the z-score for 190, it came out to be negative 0.5, right? Negative 1/2, right? I can go to the z-table, it'll give me this area in here, right? But I don't want that area, I want this area over here. So when I go to the z-table for 210, it's going to be z of plus 0.5. It's going to give me the area from here down, right? Whatever that happens to be. I'm going to make up a number. This is 0.6, this is 0.4, right? So 0.6, if I take the 0.6, which is the entire area of everything from here down, and subtract what's below 190, this area in here, what am I left with? I'm left with this area in here. Okay? You're smiling. I'm not sure if that's a good thing or not.
So you would do like, what, 1 minus 0.60?
No, not 1 minus. Here, I'm going to draw this again. I'm going to say this is the area for, this is 210. This is 190,
Okay.
right? Now, the way that the z-table works, whatever z you pick out, it's going to give you the area to the left of that, right? It's going to give you this whole area in here. So if I find the area for 210, right? Okay, if I go to that's going to be a positive plus 5. If I go to the z-table, it's going to give me this area here, the whole thing from that point down, right? Okay, now if I do it for 190, z equals 190, which is negative 0.5, right? Okay, that's going to give me the area to the left of 190, which is this. So if I take the area that's below 210 and subtract the area that's below 190, what am I left with? I'm left with this area in here, which is the part that I want. Okay? Let me actually do the numbers. Okay, let me go to the table. I go to the table. Okay, so plus, it's a negative 0.5. Negative 0.05. Negative 0.05 is 0.3085. I'm going to call that 31%. And plus 0.05 is 69%, right? So if I go back to my table, go back to my chart here, let me clear this.
You would add the 2 and subtract that from 1?
Well, hang on, I wouldn't even add the 2, hang on. right? Here's 210. Here's the mean of 200. And here's 190. Okay. The z-score here was a plus 0.5. Z-score here was negative 0.5. Okay. The area below 210 from here down was how much? Remember what it was? It was 69%, right? What about the area from 190 down? What was that? 31%. So if I subtract the 31% from the 69%, I'm left with what's between them, right? That's the easiest way to get to the end. So in other words, if I take 69%, subtract the area below 190, it leaves me with the area between them, right? Because I've
The answer is 48%.
right, it's 38%.
Sorry, 38.
Yeah. Okay, 69 minus 31. Okay, now just so you know, I want to go to Excel.
Is there an easier way to do it?
No. This, if you do it enough, this will be the easier way. If you practice it, it'll become second nature. No, you will, trust me. I've been doing this a long time.
What, is there a way to do it where, oh, you just deleted it.
I'm
Where
sorry.
you would just look at it from the mean and then you go like the portion to the left and then the portion to the right and you add those two.
Well, the problem with that is that the Z table will not give you the area to, you could have,
It only gives you the area
To
to
the
the left.
left. It doesn't give it, like, if there's a way to do it to give you the area to the right.
Yep.
We would be going through it right now.
in fact, this is not the only kind of Z table. The reason why they put a picture here is because the areas that are in the center of this table are areas that are always to the left of that Z value. That's what it's telling you when it shows you that picture, right here, always to the left of the Z value. That's what these numbers represent. There are versions of this table that look like,
The opposite.
well, not the opposite usually. I tell you.
Is that a T table?
No, that's T-table. We are way 3 weeks ahead of us. Maybe 2.5 weeks ahead of us. Not quite. No.
Sorry.
Oops, now what is this now? Why is it doing that? Oh, that's notes. That's why it did
Yeah,
that.
like I was having a difficult time completing the last couple of assignments.
Oh, okay. This should help then. I think this should help. Okay, so let me, so some of these, there are versions of this table that instead of,
To each his own, honestly, because I like doing the mean, the standard, but this is very confusing.
instead of the Z, instead of having the Z score like this, instead of having,
It's like the different situations, I don't know how to.
instead of having the Z-score and giving you that area over there, there are versions of this table that what they will do is they will give you the Z-score, the area, as a difference between the mean and the Z-score. Like that area in there. So the Z-score would be this area between the mean and here.
Okay.
Right? And then with a positive Z-score, it would be the area between here and here. And trust me, that's much more confusing than this is.
Yeah, we should jump
Yeah,
that.
yeah. Okay. There are some tables that do that instead. So that's why you always want to look at
Wait,
the,
are you gonna throw a curveball like that at us?
no, never. I only brought that up because, we had the question of whether it's ever different than that. But yeah. Okay,
And for
so.
the exam you have is, we had to use SPSS, right?
I think there is at least one problem where you have to use it. There's at least one problem where you have to use it to create do a calculation. That's unwieldy doing it in Excel. Yeah.
We did all the printouts.
Actually what I did was I gave you an output,
Yeah.
right? Which is, you could
Oh,
use,
we don't necessarily
I
have
did
to-
that.
Oh,
Yeah,
okay.
but you need SPSS to open the output.
That's right.
Oh, that's it.
Oh, okay, so then I can do the virtual.
You don't have to do anything in SPS.
No, yes, you do, don't you? You do. because
I
you
gave
have to-
you the raw data, so you could do your own calculation. but I also gave you the output. I did the calculations.
So we need the output for the-
Yes, you do, but you can do your own. You can do your own. But yeah, I think there's another problem that you need
It'll
that output.
open up even though
Yeah.
you don't have it.
No, I don't know about that. Will it?
Yeah, it did for me. I don't-
Oh, you know why? Because I think you get a 30-day grace period after you install it. I'm not sure, but I think you can
It's
run
still
it.
not up yet.
What's that?
It's still not released.
No, I buy the damn thing. I don't know if they'll ever get it. And we're already halfway, we're like 4/5 that we're a third of the way through the semester already, right? So I wouldn't, put it this way, I wouldn't hold my breath. Okay? So I mean, they're very earnest, but it's out of their control. I mean, I sit here, it's out of their control. It's above their pay grade, as we would say. So they're doing their best to encourage somebody to like deal with it, but they haven't had much traction yet. So, but at any rate, since it's only $35, you don't have to get the $45 version. You get the $35 version. At the end of the semester, I'll be demonstrating logistic regression. That's the one thing you can't do with the one that's $15 cheaper, the $35 version. But I'll demonstrate that. So you're not going to be doing it on a test or anything like that. And if you really need to, you can use a school computer or something like that to do
Yeah,
it.
that's what I was
Do we have a library here? We don't have a library here, do we?
thinking. But the graduate center does.
Yeah. Graduate Center on 34th Street, that's
Right.
okay. Well, actually, to be honest with you, you can probably use you can't, it won't work at the gates, but if you show it to the guards, you can probably go into any CUNY system building and they'll let you in with your ID as another school and use the library there. Like there's a library at Silberman on 119th Street. Yeah, on 119th Street, 3rd Avenue, 68th Street, and giant library, and there's computer rooms and all kinds of stuff. At Silverman, there's 3 or 4 computer labs down there, each one of them with like 20 or 30 machines in it. We all have SPSS and Excel and SAS and all kinds of stuff on them. So I just wanted to show you on Excel that there are functions in Excel. And the last session that we had, if you go back to week 4 or whatever it was, if you look in there, there is a couple of Excel sheets there, one of which lists the different functions and tells you if you put this in, this is what you get out. Right? So the functions you're interested in for this are going to be equals norm s dist. That's the standard normal distribution. The standard normal distribution is the Agrestes t table. It's a z table, whichever z table you want to use. That's the standard normal. That's based on a normal distribution with a mean of 0 and a standard deviation of 1. That's where all of those areas come from.
Wait, say that one more time. A normal standard.
Standard normal distribution is a distribution which has a mean of 0 and a standard deviation of 1. And based on that standard deviation, they generate this z table, the z table, right? So basically what this means is that when I put in norm s dist and then put in parentheses, as soon as I put in the open parentheses, it gives me a hint of what it wants next. It wants to know the z value. So if I put in negative 0.5, what am I going to get? The 31%, right? But same thing we got before, right? If I put in positive equals norm s dist, parentheses, wants a z-score, this I'm going to put in plus 0.5, right? Which is what that last example was, and there's our 69%.
But
Right.
we still have to add and subtract, right?
Yep, you still have to add and subtract. Yeah, except it's simple here. I can say equals this minus, this minus this, and I get false, whatever that made that. Yeah, I guess I did something wrong there. This minus this. That, bingo, right? So,
You mentioned you have a sheet on Blackboard that shows you the.
yeah, okay, I think it shows you the 4 or 5 different versions. I'll check, I'll go there right now and
Okay, thank you.
I'll look to make sure that it's there. I'm pretty sure it's there. And sometimes I put up so much junk that like, it's hard, I understand that, yeah, it's a lot of stuff, and yeah, I try and not get too crazy with this stuff. And there's another version of this, which is equals norm dist. Normal distribution, norm dist, parentheses. Except now it's asking me for the value x, the value of x. Like for instance, the example we just had, the value was 190, comma, the mean was 200. The standard deviation was 20.
Yes.
And then it says cumulative. That's asking the question true or false. Remember binomial distribution, it made a difference. True meant everything to the left, and false meant just that one out. Well, when you don't deal with normal distribution, that one is just a straight line, and the straight line really doesn't have any area. So false is meaningless here. So you always put true. Okay, and hit enter, and there's our 31%. Right? That is the value
Can you
that,
double click on that real quick?
yeah. And it's not well behaved that way.
If you
Excel is
double
always
click
tough.
on point 31, it will come up, like your function will come up.
Norm as this point, negative 0.05, 0.5, negative 0.5.
I didn't understand the difference between the two.
Why did not exactly this?
Like one was the Z one, the other one was the, but you're putting the same thing.
Equals norm, no, I didn't put in the same thing. Norm as dist,
Oh, with the X.
I put the Z-score in.
Oh.
Right? Norm as dist, I put in the Z-score, which was negative 0.5.
And you got that back.
And I got that value. Over here, I put in norm dist. I put in the value x, 190, the mean, 200, the standard deviation, 20, and true, and I got the same thing.
I get 0.
How come when
What am I
you do-
doing wrong?
How come when you did that the second time, all those other options came up and not the Z?
Without the S.
Yeah, that's
Without the S.
So the first-
Yeah, I used two different functions.
Oh, okay.
Right?
I missed
The
that
standard
part.
normal distribution only wants to know the Z-score. When you type in norm S this, only wants to know the Z-score. When you put the open parentheses, the only thing it's looking for is that Z-score. And it's going to give you the p-value or probability. When you put norm dist without the S and you put in the open parentheses, it comes up with a list of things that it wants to know. The value of X, the value of the mean, the standard deviation, and true, and it'll figure out the Z-score itself and just give you the percentage of the area to the left of X, right?
I'm not following that order in the list.
Yeah, if you look at it, you'll use that list that comes up as a guide. It's got to be exactly that direction, right? So now, interestingly enough, there are other functions. For instance, equals norm S inverse, parentheses. Well, this one, it wants to know a probability, right? So what do we mean a probability? The probability is like our 0.31, right? So I'm going to put in a probability 0.31. It's going to give me the Z-score. So that's norm S inverse. It does the opposite. You put in the probability, it gives you the Z-score.
I keep getting 0. I don't know what I'm doing.
Which one are you using? Norm S or
Or norm dist.
norm? Okay, equals norm dist,
Uh-huh.
parentheses. Now the first thing it wants is the X value, 190. Okay, 190, comma,
200.
200, comma,
20.
20, comma,
Comma true. Close parentheses.
true. Yeah, and close parentheses, 0.31. You sure? You sure that one of your commas is not a period?
I'm sure.
Show me.
Prove me wrong.
Is that, what is that from My Fair Lady? Show me. Don't speak of love. Show me.
Right here.
Okay, norm dis 190. What happened? I
don't know.
touched it. It's a
Yeah,
touch
you
screen.
touched it.
Yeah,
Oh.
make that go away. Okay. Okay, good. 190, 20, true. 190, 20.
Or is it 190, 20, 200? You said 190, 200.
No, 220. Yeah. Type it in again from scratch.
All right. Sorry, guys.
Hey, this is why we're here.
Yes.
I mean, I could just put up the video from last semester.
So you said normed is 180.
Whoa, wait a second. What does it say down there? X, right? First one's X, comma,
200,
comma,
200,
comma, true. Okay, hang on a second. Oops.
You think I need to just double click on that?
I think,
Don't tell me it's that simple.
no, I think, yeah.
Ah.
Yeah. It was
Thank
so
you.
squeezed together, all it had was one digit, the zero.
Thank you so
Okay,
much.
no problem. Okay, so, all right, so that's where we stand with that now. Okay, let me close this. Let me go back to our table here. Wow, 917, okay.
I'm sorry, so norm as in,
Yeah, let me just see right now if where it is on the Blackboard here. If it's not there, I'll make sure that it winds up there. And I think it's a previous week. Yeah, I think it's from last week. Except I got to figure out how to get back to Blackboard here. What am I doing here? Okay. Okay, there, let's go. I need to do this. I need to materials. I need to go here. Okay, let's look in here. The Excel functions, here we go. There you go. Norm as dist. Put in the Z and it gives you the p-value, the area to the left of Z. Norm dist, X, mu, sigma, and true. You put that in and it gives you the area to the left of that value X. Norm inverse, put in the area, P, the probability area, mu and sigma, and it gives you the value of X. Norm S inverse, put in P and it gives you Z, right? And I even gave you, I think, oh no, what did I do here now? Tell me I didn't, oh, here, okay. I even gave you an Excel file with the same thing, with the values. Oh no, it's the same thing. Yeah, it's just the same thing. So you could, so you, if you want, you could practice on here, right, with things, staring in the face. Okay. Play around with them. I mean, this is like, in order to really learn this stuff, you really have to exercise it a little bit. Okay, so now let's go back to where we were before. Let's see now. Let me see where my Word document went. There it is. Oh, no, that's not the one I want. Oh, but I closed it. No.
That one right.
What's that?
No, you had to go.
I want to go here. That's the next example sheet. The one I want. I didn't get done with the one I was working with. I'm going to post a copy of a lecture, one of Levi's lectures, that goes into this as well. So you'll have the lecture to look at. I don't have it on there right now. All I have there is a PowerPoint right now, but I'll put a recording of it on there too, so you have that as an option. Also, this is an old version of this lecture from last fall. I'll give you, in addition to our version of it now, I'll give you access to that one as well, in case maybe I did a better job that time. It happens. Okay, lab exercises. Okay, and let's see, confidence. Yeah, this is the one I wanted. Okay. Okay, now we're going to apply the central limit theorem. You take a sample of size 25 from the population above. What was it again? The mean of the population was 200. The standard deviation was 20 of the population, mu and sigma. You take a sample of size 25 from that population. What's the probability that the mean of the sample is larger than 204? Gee, what's going on here? Let's think about what's going on here. I'm going to take a sample of size 25 from that population. And then I want to know what's the probability that the mean that I get from that sample is bigger than 204. Okay, so how am I going to do that? Let me draw this again. I don't want notes. Why do I keep clicking that? I want this. Yeah, nice blank piece of paper. Okay, so the original population looks something like this. The mean is 200 mu, and the standard deviation is equal to 20. Now, if I take repeated samples of size 25 from this population, I'm going to draw a little bit wider. If I take repeated samples of size 25 from this population, what do those, say take 1,000 times, right? And I create a new normal distribution from the sample means, not just the individual people, but from the sample means of size 25, I make a new distribution, okay? That's going to be narrower, right? The mean, half the time we're going to get over 200, half the time we're going to get under 200, but the mean of our sample distribution is going to be 200, just like the population. However, the standard deviation of our population distribution is not going to be 20. What's it going to be equal to? Sigma over the square root of the sample size. And what was sigma? Sigma was 20 divided by the square root of the sample size. 25 is 5, and that's going to be equal to 4. So this is a distribution of all the samples that we're going to get if we repeatedly took samples over and over and over again. So now the question is, what's the probability? Let me get back to the question so I can show it to you. What's the probability that the mean of a sample that we took from this population would be bigger than 204? If you asked me, what's the probability that you would pick a single individual from this population whose cholesterol is more than 204? Well, the z-score would be 204 divided by 204 minus 200 divided by 20 is equal to 4 over 20 is equal to 4 over 20 is 1/5. It's 1/5, right? Is equal to 0.2, right? Plus 0.2, right? In other words, this area here would be like 48% or something like that, right? Because only a little bit above the mean, right? Okay, but now, what if I asked you, what's the probability that you took a sample of size 25? The probability that your sample mean would be greater than 204, right? Would be this area. Well, let's find the z-score for that occurring. So the z-score is going to be equal to 204 minus 200 over, what's the standard deviation for the repeated samples? It's only 4, is equal to 1. So the probability that we would get a sample that is greater than 204 is the area below z-score of 1 subtracted from 1, right? So I'm going to go to our table. So whoops, that's the wrong table. Let me close that. We don't need that anymore. Oh, I don't have a pointer. Okay, here's our Z table. So z-score of +1 is going to be 0.8413. Oops, wrong one. This is This is 0.8413. So that would leave this area to be 0.1587, about 16%. Right? That's the probability I would get that. So now all of a sudden we can predict based on what we know about samples, what we know about the population standard deviation, and how the sample standard deviation, we can predict how likely it is that as we increase the sample size, that we would get a value that's that far away from the population mean. So if the sample size had been 100, what would have happened here? It would have been 20 over 10, which would be equal to 2. So 204 minus 200 over 2, z would be equal to 2, right? Which would mean that this area over here is only going to be like 2.5%, right? Why 2.5%? I'm sorry, this area over here would only be about 2.5%, right? It'd be above a value of 204 because it gets narrower and narrower and narrower. The likelihood of getting a value that's far away from the mean, the population mean, becomes less and less likely as you increase the sample size.
Can you repeat that one?
Yeah.
Sure. As you increase the sample size, the probability of getting a sample mean that's dramatically different from the population mean gets less and less likely because the distribution of all the possible samples that you might take becomes narrower, right? So it comes narrower and narrower, it comes closer and closer to what the actual mean really is. We can use this, and ideally, we would love to be able to say, let me just clear this, erase this. So how can we take advantage of this? We would love to be able to say, hey, I took a sample from this population, mu is equal to 200 and sigma is equal to 20. I took a sample from this population and I knew that sample size is equal to 25 and it came out to be a certain value, right? And let's say it came out to be, I don't know, 201, something like that, right? So X bar, right, for our sample came out to be 201. How do I know how close I am to this population? Well, if I know even if I don't know what the mean is, let's say I don't know what the mean is. How do I know that 201 is close to what the mean is, right? How close is it? What kind of assurance I got that it's close and how close is it? Well, I don't really know that. I'll never really know that because I'll never really know what the mean is. So in other words, when you do studies, when you take a sample, will you ever know what the true population mean is? No, right? That's unattainable, right? So you never find out. That's something you're never going to find out. But you want to have some assurance that when you take a sample of size 25 or a sample of size 100, you want to have some assurance that mean that you got from your sample really approximates the population means. But you really don't have that assurance because you don't know what the population mean is. But what you do know, if you have some idea of what the standard deviation, the variability of the population is, you know that as the sample size gets bigger, then then the samples that you take, repeated samples, would be closer to the population mean. Less variability within those repeated samples. So even though we can't say for certain how close we are to the population mean, what we can do is we can say to ourselves, well, if I take a sample of size 25 and the standard deviation is equal to 20, right? Well, let me think about this. Let's say if it's 20, if I get a 201, right? And I know the standard deviation is equal to 20, and my sample size is equal to 25. My sample distribution, standard deviation, is going to be equal to 20 divided by the square root of 25, which is equal to 20 over 5 is equal to 4. So you know, at 201, if I assume for a moment that that's the real population mean, well then, you know, I would expect samples to be around that. And if I look at the standard normal distribution, if I look at the empirical formula, it tells me that, you know, if I go 2 standard deviations to the left and 2 to the right, that's 2 standard deviations. Uh, uh, that's 8. So that's 201 minus 8 is 193. And added to that is 210. I'm 95% certain that any sample that I would take from a population has that, I would expect my sample mean to be within 2 standard deviations of this with at least 95% chance of being right. I would only expect that I would get a sample that's so far from the true population mean, 2.5% of the time below 2 standard deviations and 2.5% of the time above uh, 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 the sample mean. So what does that tell me? What does that tell me? That tells me that if I'm willing to be only 95% certain, that's pretty good, right? 95% certain. Instead of saying that I know how close I am to the true population mean, instead I'm going to say that my 201 that I got from my X bar, my sample mean of sample size 25, I'm going to say that if I go 2 standard deviations above and below the value that I got, I'm 95% sure that the true population mean, which is unknown to me, is within that range, right? So 2 standard deviations, if the sample size is 25, that's plus or minus 8. That's 193 to 210. If I increase my sample size to 100, that becomes 2. 2 times 2 is 4. So that would be 196, 197 to 205. I'm 95. See, as I increase the sample size, the range within which I'm 95% sure the true population mean exists gets narrower. Anybody know what would be a good name for this interval here? That we're 95% sure that the true population mean exists? It's confidence interval. That's the 95% confidence interval. So when you read these studies that say that exactly, so when you read a study that says we took a sample of 50 children in the Bronx and we found that their average blood lead level was 5.6 micrograms per deciliter of blood or something like that. And then in parentheses, confident 95% confidence interval 3.2 to 7.6. The actual average they got for their sample of 50 kids was that, whatever I said, 5.1 or something like that, right? But because of the variability, because of the sample size and the effect that has on standard deviation, they say, the average we got was 5.1, but that's for those 50 kids. Now, if we're looking at the entire population of kids in the Bronx, now our confidence interval for the true population mean is now within these two numbers. That's how we use that. Yes?
So that average of 201 is for the sample size of 25.
No, the 201 is the average I got from my sample of 25 people.
Okay, right. And now
And the plus or minus 2 times the standard deviation is and why did I use 2 times the standard deviation?
because it's
95%. I told you a lie last week. Remember I told you about the empirical formula? And I said 95% of the population is in a normal distribution is between 2 standard deviations below the mean and 2 standard deviations above the mean, right? I was lying. That's an approximation. What is it really? What is it really that has 95% between those two? Where's a good spot where we can find out what the actual area is? How about the Z table? Okay, let's look at the Z table. I want to know what area gives me what Z score gives me 2.5% here and 2.5% up here. So I'll start down here, 2.5%. So I'm looking for the area that represents 2.5%. Okay, here we go. So 2.5%. So these are the areas, right? So 2.5%, 2.205. This is 0.0250. If the empirical formula were accurate, this would be 2 standard deviations. Is it 2? No, it's not. It's actually 1.90123456, right? So really, in real life, the area, the range of standard deviations that represent 95% of the samples, right, is actually not 2 standard deviations. It's actually minus 1.96 and plus 1.96, not 2. That's more accurate. So what does that mean our confidence interval for the problem I just solved is? I took a sample of size 100, right? Standard deviation of population was 20, right? So the standard deviation of our sample distribution is equal to 20 over the square root of 100, which is equal to 2. So now if I want to find my confidence, when I take my sample of 100, my mean was equal to 201. I don't know what the actual mean is. I don't know what mu is. But I can say based on that sample that I took of that came out 201, I can say I'm 95% certain that the true population mean is between X bar plus or minus 1.96, not 2, times the standard deviation of the sample distribution, not of the population, right? You know, think how inconvenient this is. It's a real pain in the butt. I'm calling both of these the standard deviation. It's going to be easy to get it confused. Instead of calling the sample mean, the distribution of the sample means, instead of calling it a standard deviation, I'm going to call it a standard error of the mean. Call it standard error of the mean, standard error. It's the standard deviation of the samples, repeated samples, where you're going to give it a new name called standard error. So it's going to be 1.96 times the standard error. What's the standard error equal to again? Sigma over the square root of the sample size. In this case, 2. In this case, 2. So what is this? It's 201 plus or minus 1.96 times 2, which is 201 plus or minus 4.3.82, right? Which is equal to, on the high end, the easy side, 204.82, and on the other side, whatever it comes out to when I subtract.
How did you get 2 as the standard error? Is that just a number that?
I got that because I knew the population standard deviation. This only works if you know the population standard deviation.
So all the time when you were saying that's the standard deviation of the sample, it's actually a standard error.
It's called standard error. It's the same thing. It's, in other words, it's the square root of, it's standard deviation of the population over the square root of the sample size gives us the standard deviation for repeated samples of that same size, that new distribution. Okay, and that, just so to avoid confusion, instead of calling it standard deviation of the sample, repeated sample means, we call it the standard error, just to avoid confusing it. Okay, so now I just told you something that's a deal breaker here, didn't I? I said, in order to make this work, we got to know what the population standard deviation is. How do we know what the population standard deviation is? Huh? Yeah, well, you don't know what the sample mean is. You don't know what the standard deviation is. You don't. You're never going to know that either, right? So, you know, for now, we're gonna be satisfied with making believe we know that. In fact, we really don't know it, but we know a good way of approximating it, right? How do we approximate the standard deviation of the population mean? Remember, we just did it before by taking the sample standard deviation. the standard deviation of the 25 people we sampled approximates the standard deviation of the population, just like it approximates the mean of the population, right? Remember that? Remember we got close to 50 and close to 9 when we just did an average of 9 people, right? So we're going to do that. That throws a kind of a monkey wrench into our calculations. We really don't know this confidence interval with 95% certainty, at least not using this 1.96. That's where the t-table comes in. The t-table corrects for the uncertainty that's introduced by not knowing the true population standard deviation. We're going to forget I said that because that's, I think, a week or two away. Okay. Okay, so now I'm gonna do one more thing just to throw it at you. See if it sticks to the wall. Like spaghetti. Okay, I'm gonna do one more thing. Okay, and that is, I just wanted to mention to you that we can do this with proportions also. Okay, so for instance, I can say to you that, let's say that I don't know, Joe Biden, right, has let's say that we have a poll that of 1,000 people, and in that poll, we want to know whether the majority of people in the United States approve of a impeachment inquiry. Okay, so we take a random sample of 1,000 people in the United States, and we find that 510 people out of 1,000 approve of an impeachment inquiry. Is that really what the entire country thinks, though? Okay, well, how do we know? We don't know that yet, right? So what proportion of the population, based on this sample, does it appear approves of the inquiry? Well, it's 500, 51%. 510 over 1,000 is equal to 0.51. Okay, so maybe we can do the same thing that we did with our population proportion, with our population mean, our sample means, to determine a confidence interval for proportions. So in order to do that, we would have to say to ourselves, okay, so what's the formula going to be for this? I'm going to say P cap. Okay, I'm going to call this P cap. Whenever you see P, that means population proportion. Just like with X bar, whenever you see P cap, it means sample proportion, right? So I'm going to say P cap plus or minus 1.96. Why 1.96? Because that represents our 95% times our standard error. So now I need a way to calculate standard error for a proportion. So the standard error for a proportion is equal to the square root of P times 1 minus P over N. Okay, that's cool. Let's see what that comes out to. Standard error is equal to the square root of 0.51 times 0.49 over 1,000. Okay, I'm going to actually calculate that out. My calculator. Oh my goodness. Oh, look at that. Okay. 0.51 times 0.49.
Why did we put 100?
1,000. I made a mistake. Divided by 1,000. I ran out of ink. Divided by 1,000 is 0.000249. I'm going to take the square root of that. And it comes out to be 0.0158. I'm going to call that 0.016 or 1.6, right? 1.6%. So what is that? P cap, our confidence interval for the true population proportion, right? 0.51 plus or minus 1.96 times P cap, which was 0.016. Okay, now I could multiply this out, but I'm just going to multiply by 2 instead of 1.96. 0.51 plus or minus 2 times this would be 0.32. So our 95% confidence interval, we're 95% certain that the true population proportion that approves of an impeachment investigation is 0.542, 54% between, and we got subtract 3.2, which would give us 0.478, right? Between 47.8 and 54% is our 95%. So do we know with 95% certainty that a majority of people in the country approve? No, we don't, right? Because we're 95% certain it's between 48 and 54%. But in order to be able to say with 95% certainty that that the majority of people approve of this, this would have to be great. Both of these numbers would have to be greater than 50% for us to be 95% certain that the true population proportion is bigger than 50%.
Are you you're just adding and subtracting
Point-
0.31 from
0.32.
0.032?
Yes, exactly. That's just like we did before with a mean, adding and subtracting. Basically 2 times the standard deviation or standard error.
2 questions.
Yes.
Where did you get the 1.96 from?
That was our Z, that's a Z score, Z table. Remember, that's a Z value, 2 standard deviations. Remember, 95% of the results.
So you're always going
in the normal.
So in that equation, you're always going to use 1.96.
Yes,
Okay.
for a 95% confidence interval.
Or 95%. Okay.
Now, let's say that you wanted to be more certain and you wanted a 99% confidence interval.
You just go back into the.
You go back into the Z table and you look for 99 means that you got to have a 0.5% on either end, right? So let's see what that would be. So 99% less than less 0.005, 0.005. Let's see what's the closest to that. Looks like this be negative 2.5. Looks like about negative 2.5. Negative 2.5. I'm blotto from looking at this. Negative 2.58, it looks like. Let me try this again. 0.05, 0.5%, 0.005. Yeah. 2.58, 2.57, 2.58. Usually most people use 2.58. So what would that mean if I use 2.58? Right? If I use plus or minus instead of 1.96, 2.58, if I use 2.58, what does that mean? What happens to the number that I add and subtract from 0.51? Does it become smaller or bigger?
Smaller.
2.58 times this becomes a bigger number than 3.2, right? And since we're adding and subtracting that bigger number, it makes our confidence interval wider. That makes sense. Because if one of the things that you can do to increase your confidence that you've captured the true mean is by making your confidence interval wider. So a 99% confidence interval is wider than a 95% confidence interval. How about a 90%? If you're willing to be only 90% certain, it's narrower, right? And what number would we use then? We would use 1.64. Why 1.64? Because if you look on the Z table, 1.64 represents 5% in either tail. In other words, 10% chance of being wrong, the true mean being outside of the range that you picked, right? Okay?
Just one final.
Sure.
That SE, in the previous, we used the formula of sigma over the square root of n.
Right.
Why did it get changed to?
This is for proportions. This is strictly for proportions. Remember we also had, for instance, the for the binomial, the normal approximation binomial distribution, the standard deviation we use is n times p times 1 minus p, right? Square root of that, right? So it's another way of calculating standard error. And by the way, when we get into working with the t-scores and stuff like that, with proportions, we almost always use 1.96 or 2.58 or whatever we want to use from the z-table. We don't worry about the fact that we don't actually know the population standard deviation, because typically with proportions, we're working with the very large samples, like with polling and stuff, like you're working with very large samples. So you don't worry as much as you do. Remember I told you the caveat was that only works if you really know what sigma is. If you don't, then you got to make some accommodations, which we'll be doing later on. We don't have to worry about doing that now. But with proportions, we're always working with large sample sizes.
So one other, so when you say 0.478, 542, what that means is like with 95% certainty, you believe the country supports impeachment with 95% confidence, you believe
The true
0.8, 54, 0.2%.
is with 95%, we believe that with 95% certainty that the actual proportion for the entire population is between those two
Yeah,
numbers.
that's what I meant, right.
Right.
And then if it's 99, it's wider because you're like, with 99% certainty, we believe it's between these areas.
Right. What you've done is you made your range wider, so that makes you more confident that the true population proportion is in there somewhere.
Right. Okay.
Right. And really what I would want to see there, if I would want to be able to say with 95% certainty that the country is really in favor of this, what I would have wanted to see was that the confidence interval is, say, 0.51 to 0.59. What does that tell you? We're 95% sure it's between these two numbers. Means
Right.
we're also 95% sure it's greater than 50%. Right. In other words, if I told you that we are 95% certain that the proportion of the population that wants an impeachment investigation is between 51% and 59%, isn't that the same thing as saying we're 95% sure it's bigger than 50%? Right? Get it? Okay. But since it came up that we're 95% sure it's between 48% and 54%, we can't really say that we're 95% sure that it's greater than 50%, because it could be 49, could be 48, 48.2, right? And still be within our confidence interval, right? So we can't be certain, we can't have 95%. So see what we're trading something off here. We're trading knowing how close we are to the actual mean. We're trading that for a different kind of knowledge, a kind of knowledge where we can predict how likely it is that the true population mean is between a certain range. Okay, later on, we're going to be talking about if you do this with two populations, and the mean blood lead level for children in the Bronx is between 3 and 7, but for children in Queens, it's between 8 and 15, right? The two confidence intervals don't overlap, right? So you can say, gee, it sounds like it's different. But if they overlap, it could be just those two samples you happen to take, happen to be a little bit, they're always going to be different, right? Question is the population level different, right? Population mean different. And since they overlap, you can't really be 95% certain that they're really the true population means for Queens and children in Queens, equivalent in Bronx are really different. You usually don't use confidence intervals quite that way. Use something else called a t-test. When we get to it, we'll do that. But you can kind of use this to kind of wrap your head around the idea of what a confidence interval is. Don't tell anybody that I ever told you that you can use confidence intervals that way, overlap and not overlap, to compare two populations, because that's like verboten in statistics. Even though it kind of makes a little bit of sense, intuitively, that's bad practice. You want to you use a t-test to determine that. And a t-test is just another way of doing these confidence intervals and looking at the differences between the two means you got for the one population and the other population. Yes?
Silly question. Shouldn't we have always been using peak cap?
Yeah, I should have, I gave up on, yes. Well, actually, the standard error is equal to P times 1 minus, that's technically the formula for it. But since we don't know the population proportion, we're assuming that it's, yeah, that's all we got. We're using what we got, right? Just like sigma, the square as sigma over the square root of n, right? Later on, when we're using the sample standard deviation instead of population standard deviation, we're using it because we don't know the population. We're never going to know the population standard deviation for certain. So we're stuck using the sample standard deviation instead. Okay, same thing with the proportion. Okay, I think it's a good place to stop. I will put up a copy of, I will make available, I don't think it's available actually for you right now. I'll make available the same version of this lecture from a previous semester in case it works. And that one that was probably a 3-hour session. So it might have a little bit more, but I'll also make one of Levi's formal lectures available also, so you can see kind of a little bit more of the theory. And also he covers something we didn't get to, which was types of studies, okay, cohort and so on and so forth. That's important to you guys. When you go into epidemiology, like the types of studies, what kind of studies they are, which ones are appropriate for different kinds of situations.
Important for this class.
Yeah, they're kind of important for this class, but less so than an epi.
If I don't have to know it, I don't want to study it.
Chances are it won't come up beyond what the lecture.
Awesome.
In other words, I probably won't put on exam, at questions about study types necessarily, but you'll hear me talking about it during the semester.